Hello physics students, this is Dr. Brenzi here, and our objective for this lesson, which is lesson 6.1.2, is that we're going to be able to calculate how fast you need to go to escape Earth's gravitational pull. Now, so if you've ever thought about how, gee, I want to get off this planet, well, by the end of this class you'll be able to figure out how fast you need to go in order to do that. So let's get started. I want to talk about gravitational potential energy because it plays a role in calculating how fast we need to go in order to escape Earth's gravitational pull. We're used to using this formula for gravitational potential energy, which we learned way back in Unit 3, and that is that the potential energy of an object is its mass times little g times its height h. Okay. So, if we have two objects, and one of the objects is higher than the other, then we know that the one on the left has lower gravitational potential energy than the one on the right. Okay. Now, when you start to talk about things as big as planets and stuff like that, we have to change this gravitational potential energy formula. Oops, let's see here. What do I have going on here? All right, so we have, for example, let's take a satellite that we have orbiting around a planet with mass, big M, and it's at a radius of r away from the center of mass of the planet. Well, it turns out that if we start dealing with large objects and things out in space, that we use a different formula for gravitational potential energy. And it turns out that gravitational potential energy out in space and things that are large distances away from planets turns out to be negative capital G, big M, little m, divided by r. Now this looks a lot like the formula for force, right? Yeah, it does. The only difference is now that we have r to the first power in the denominator instead of r to the second power in the denominator. So try not to get those two mixed up. You'll get used to using both of them back and forth, and hopefully by the time we've had enough practice, you'll remember that potential is r to the first power in the denominator and force is inverse squared, or r squared, in the denominator. All right. Well, so let's say we have, now the reason we use this formula, I want to explain that, and I want to explain, does it work like gravitational potential for a ball that we throw up in the air, that MGH formula? Because this looks a lot different, doesn't it? Well, to kind of explain to you that it does work similarly to gravitational potential MGH that we're all used to so far, let's take a planet X. So let's call this planet Planet X. And let's say that just by pure luck or coincidence, that when you multiply G, which is our universal gravitational constant, 6.67 times 10 to the negative 11, and you multiply that by the mass of the planet, and you multiply that by the mass of the satellite, it just turns out that it's some weird coincidence of nature that it's equal, those three things when you multiply them together equal 10 to the sixth power. Now it doesn't really matter what this mass really is and what that mass really is in order for me to demonstrate my point. So I'm going to use this number for everything in my numerator up here. So let's go to planet X. And let's say that our satellite is a distance of 10 to the 7 meters away from the center of planet X. Okay. So when I plug in this into my formula for gravitational potential energy out in space, it turns out I get 10 to the 6, that's this number right here, divided by 10 to the 7, and that turns out to be negative 0.1. So this satellite orbiting this planet at this distance has a potential energy of negative 0.1 joules. Now you might be wondering about the negative sign, but hang in there with me and I'll explain it to you on my next slide. Well, let's take a satellite and let's move it half the distance. Half the distance between the center of the planet and this distance. So let's put it right there. And that distance turns out to be 5 times 10 to the 6 meters. Now, if you're not sure why in the world, if when you go half, excuse me, got a little coughing fit there. Why is it that when you go half the distance, this number, instead of becoming 0.5, becomes 5? Well, that has to do with scientific notation. So if you're a little rusty on that, well, if I take 0.5 times 10 to the second, and I hope you can recognize that this is 1/2 times this number, well, what I can do is I can say that this is the same as 0.5 times 10 to the 6th. In other words, I'm taking one of these factors of 10 and I'm pulling it out. And then if I multiply 0.5 times 10, I get 5. So half of this is indeed 5 times 10 to the 6th. So I hope you're convinced that by using this for r, I am actually half the distance that I was originally. Alright, so I plugged that into my potential energy formula here, and it turns out when I do that, I end up with negative 0.2 joules. So when I'm farther away, I'm at negative 0.1 joules, but when I get closer to the planet, this becomes negative 0.2 joules. Well, wait a minute, that doesn't quite seem right unless you recognize that what we're dealing with here is negative numbers. We're no longer dealing with positive numbers. So, let's think about this. We had a picture where if something was close to the planet, close to the ground, it had a low potential energy. Well, our satellite that was closer to the planet had a more negative number, and a more negative number is less than a smaller negative number. Okay, so it's still true that when you go further away from the planet, you get a higher value of gravitational potential energy, but higher means less negative. Lower potential energy means more negative. So increasing distance, r, makes gravitational potential, UG, increase. In other words, it makes it less negative. Okay, so this formula for gravitational potential energy out in space still works the same way that we're used to with gravitational potential throwing a ball up in the air and watching it come back down. We still have low gravitational potential energy when we're close and high gravitational potential energy when we're far away. It just is a matter of remembering that this is low means more negative, high means less negative. Okay. Now those of you in AP, I have another proof for you, and it's a proof that involves calculus. So, if it is true, well, first of all, we do know that this is always true. This always holds that the force due to our gravitational potential is equal to the opposite of the derivative of that potential with respect to distance. Okay, and in our case, distance is the radius away from the object. So if I set up this equation here, and let's take this potential energy that I just proposed to you. Oh, we're going really fast here, aren't we? Let me back that up. Okay, and let's take the derivative of this new potential energy with respect to r. So I'm going to take ddr of all of this. Okay. And when I do that, I end up with, stop it, Dr. Brenzy, stop going so fast. Well, I end up with g big M little m over r squared. But remember that the force is opposite of that derivative, so I still have this negative sign on the outside, which means my force is equal to negative gmm divided by r squared. And that is, for those of you in AP, this negative sign is consistent with having a negative gravitational potential energy. Okay. All right, so those of you who are taking advanced physics, welcome back. So we have, now we have to talk about escape velocity. So, like I said in the objective, like how much velocity do I need to get off of this planet? Well, it turns out that, well, go ahead and write this question down. When does an object have enough kinetic energy to escape gravity? And that's another way of saying, what velocity do I need to escape this place? Because, you know, sometimes you just want to get away, right? I think that's Southwest Airlines. So, it turns out we know that total amount of energy that something has is equal to its kinetic energy plus its gravitational potential energy. So in this case, its total energy is equal to 1/2 mv squared minus big G, big M, little m, divided by r. Now, those of you who are in advanced class, I'm not going to actually have you memorize this formula or anything like that. So if you don't want to take notes until we get to the final formula, that's all right. AP, though, you guys got to stick with me. You got to understand how we come up with this formula. But advanced physics, it's good enough to understand that, hey, it follows that when you take total energy equals kinetic plus gravitational potential energy, that we're going to end up with an escape velocity. Because it turns out that when your total energy is less than 0, then the object that we're talking about is bound or it's captured by Earth's gravitational pull. So when this sum is less than 0, we can't escape Earth. It's impossible. If we try and we throw ourselves up as fast as we can, if our total energy is less than 0, according to this formula, then we are simply going to be we're going to end up not going anywhere eventually. And we're still going to be captured by Earth's gravitational pull. But it turns out that if we have enough kinetic energy so that this sum is greater than or equal to 0, then we can escape. Well, so that's the principle. So let's say we know that escape happens when the total energy is equal to 0. So let's set up this equation that 0 equals 1/2 mv squared minus G big M little m over r. Well, if you add gm m over r to both sides, you get an equation like this. We have little mass on both sides, so that'll end up dividing out. We can multiply both sides by 2, and we end up with 2gm over r equals v squared. And when you take the square root of that, you end up with an escape velocity equal to the square root of 2gm over r. So this is how much velocity you would need to escape Earth's gravitational pull. All right. So if you ever want to get away from this planet, this is how much velocity you need. Now you know. Let me give you an example problem, and I want to erase that because I thought I was going to teach something and decided to teach about gravitational potential energy instead. So we have a 1,000 kilogram weather satellite, and it's in circular orbit, 300 kilometers above Earth, and we're going to calculate its gravitational potential energy. So let's do that. We have our formula, and I'm going to plug in G, 6.67 times 10 to the, negative 11. Oh my goodness. This is totally going to change my answer because I totally forgot that until just now. That's a negative 11. And then we have 6 times 10 to the 24. And then we have, that's the mass of the Earth in kilograms. And then we have 1,000. That is the mass of the satellite. And then we have to divide that by r. Now r, just like with force, is not just 300 because this is 300 kilometers above the Earth's surface. So if we think about it, our weather satellite's above Earth 300 kilometers, but that just means that this distance right here is 300 kilometers. Don't forget that we have to go all the way to the Earth's center of mass, which means we have to add to this the radius of the Earth. Okay, so in my denominator, I have to take the radius of the Earth, which turns out to be 6.4 times 10 to the 6 meters, plus 300 times 10 to the third, because that's how much 300 kilometers is. Okay, so we have, let's see if I have enough space to fit this in. We have the radius of the Earth, let me back that up, radius of the Earth, plus 300 extra kilometers. Okay, and that's what this is on the bottom. All right, so, I might run into my own writing here. Okay, well, I'm going to run into my own writing, so I need to erase this. You can keep this written down, but I need to erase it before I can go on. So let me do that very quickly. All right. So, let's see, if I had done my math correctly, it's not 400 times 10 to the 38th like I thought. I actually have to change that. Oh boy, so if I take that minus 22, 30, minus 22, I come up with 16. So negative 40.0 times 10 to the 16, when you multiply that times that times that, okay, and you can try that in your calculator. By the way, one way to do that is to multiply the numbers out front, 6.67 and 6. When I multiply the numbers out in front, I get negative 40.0. And then, with scientific notation, you can just add these exponents. So if I take negative 11 plus 24 plus 3, well, that's negative 11 plus 27. 24 plus 3 is 27. Well, negative 11 plus 27 turns out to be plus 16. So my exponent in my scientific notation would be 10 to the 16. And then we're going to do the same thing now with the denominator. When you're adding scientific numbers together, remember that you have to have the same exponent. So I need to change this number so that it has a power of 10 to the 6. Well, when I do that, I get 0.3 times 10 to the 6. And if you're not convinced of that, you move this over 3 decimal places, 1, 2, 3, and those 3 additional decimal places give me 10 to the 6. So I have 0.3 times 10 to the 6th. Now that I have the same exponent, or power of 10, now I can add these together. So if I take 6.4 plus 0.3, I get 6.7 times 10 to the 6th. All right. Now, when I want to divide two numbers in scientific notation, I take the quotient of the coefficients, the numbers out in front. Well, 40 divided by 6.7 turns out to be negative 5.97. And what do I have to do with the powers of 10? Well, I have to subtract them. So I have to take 16 minus 6, and I get 10 to the 10. Not 10 to the 32, but it's 10 to the 10. All right. So it turns out that this is going to have a gravitational potential energy of negative 5.97 times 10 to the 10 joules. Okay, when you come into class tomorrow, I'm going to expect you to be able to work through an example similar to this on your own. And then we're going to do some group problems on how to apply both gravitational potential energy and how to apply escape velocity to a variety of problems. So I'll look forward to seeing you then. Bye.